In this video, we are going to solve a problem from exercise 1.3 of chapter number 1 number systems, and we are going to look at question number 4. Let's read the question. Express 0.999999 dot in the form p by q. Okay, so we all know that p by q is nothing but a rational number. Okay, p by q is nothing but a rational number, and this decimal expansion, okay, it is non-terminating. This decimal expansion is non-terminating but recurring. It's non-terminating plus recurring. So we know that if a decimal expansion is non-terminating and recurring, then it is a rational number and it can be expressed in the form of p by q. So let's see how we can express it in the form of p by q. So let x be equal to 0.9999 dot in the form of in a short form we can write it as 0.9 bar. Okay, this bar indicates that this digit is repeating indefinitely. Okay, now what we do is we see the number of digits under the bar. The number of digits under the bar is 1. There is just one digit under the bar, so we multiply both the sides of equation by 10. So I'm going to write it down. Multiply both the sides of equation by 10. Why are we multiplying by 10? Because the number of digits under the bar is 1. If there are 2 digits under the bar, then we multiply by 100. If there are 3 digits under the bar, then we multiply by 1000, so on and so forth. So let's see what happens after the multiplication. After the multiplication, we get 10x as equal to 9.9999 dot. Okay, and now this can be written as 9 plus 0.9999 dot. Okay, so the trick here is we have to express this in the form of a plus x. Okay, where x is our the number which we have assumed at the start of our video, and a is some number. So x will be this, which is 0.9999, and a is some valid other number. And now thus if this is x, then we just substitute the value of x. So I'm going to continue. So this is going to be, so 10x is equal to this, that is going to be 10x as equal to 9 plus x. And now we're going to rearrange. So we are going to take x to one side of the equation, so that's 9x as equal to 9, and thus we get x as equal to 9 by 9, that is equal to 1. So we have got x as equal to 1, but what is x? X is equal to 0.99999, and x is equal to 1, like 9 by 9, which is equal to 1. So we observe that although this is, so 1 is a valid natural number or a whole number, and this is 0.99999. So 0.99999 is actually a number which is very close to 1. So in the form of rational number, it becomes 1, or you can just say 1 by 1 rather. Okay, so if you draw a number line, let's draw a number line. Okay, let's say this is a number line. Okay, and on this number line we have here 0, and we have here 1, and we have here 2. So this number, this 1 by 1 is exactly here, and 0.99, if we zoom in, 0.99 is going to be very close, very close to the 1, because it's 0.9999 and it's like infinite. So 0.99999 is going to be extremely close. I can't zoom in further. It's going to be very close to the number 1, but it's not equal to 1, but it's very close to the actual number 1. So in the form of rational number, when we want to express 0.99 in the form of p by q, it basically comes down to 1 by 1. Okay, so this is how we can express 0.99 into a rational number. Now let's go to a next question. From the same exercise 1.3, we are going to see now question number 5. Let's read the question. What can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? So 1 by 17 is a rational number of the form p by q, we have to find the decimal expansion or a decimal representation of this rational number. Perform the division to check your answer. So let's start with it right away. We have to perform the division 1 by 17. So I'm going to write it like this. 17 is my divisor and 1 is my quotient. So for this we are going to need the help of a table of 17. So I've already noted it down here. This is our table of 17. 17 into 1, 17 into 2, so on and so forth. So let's start. So first of all is going to be okay. First of all is going to be 0 point. So this is going to be 10. Okay, and then is going to be another 0. So this is going to be 100. And now for 100 we have 102. We can't take 102, so we have to take 5. So it is going to be 5. Okay, and this is going to be minus 85. So 100 minus 85 is 15. Okay, and then one more 0, which is 150. And now as you can see, we have to go with 136, so 8. So I'm going to write here 8 and minus 136. So the remainder is 14. Again one more 0. Now for 140 we can again go for 8, 136. So let's continue. This is going to be 8 and then we get 136, and again 4 is the remainder now, and then we get 40. Now for 40 we have 2, which is 34. So let's go with 2. That's minus 34, and what we get is 6. So once again 60, and for 60 we have to go with 3, which is 51. So let's continue. 3 and minus 51, so the remainder is 9. Let's zoom in. Okay, so for 9, let me just okay, now we have 9 as a remainder, so 90, and for 90 we have to take 5, which is 85. So okay, let's continue. This is 5, so minus 85, and now 5 is the remainder, and then once again we go with 50. 50 is once again 2. Okay, which is 34. So 17 2s are 34. Now the remainder is once again 16. Remainder is 16, and then we get 160. 160 will be 9, which is 153. So as you can see, the repetition is not yet coming. So it's minus 153, and the remainder is 7. And then we again put 70. Now for 70 we have to go with 4, which is 68. So let me put here 4, and this is 68. Now I'm going to continue here. Okay, let me continue here. So 68, and the remainder is 2. So we get the remainder as 2, and let this will be 20. And then again we'll have 17 ones are 17, so it's minus 17, and we get 3, and then again 30. Then again 17 ones are once again 17, and the remainder is 13, and 13 turns into 130. 130, this is again 7. Wow. So 17 sevens are, it's minus 119. So the remainder is 11, and once again I put a 0, then 110, and now for 110 I have to go with 6. So I'm going to put here 6, and it is 102, and the remainder is 8. Wow. So still now we have not got any repetitions of any of these digits. Okay, here you can see these are all different digits with no repetitions. Now we have to really zoom in. Okay, now this is 80, and for 80 we again have 4, so I'm going to put here 4, and this is going to be 68, and the remainder is 70, 12. So 120. For 120 we have once again 7, which is 119, and oh, finally we have got 1. We started with remainder 1. We started with 1. So here once again we have 1. Got it? And then we are going to make here 10, and then we are going to add one more 0 here. So that's going to be 100. And once we get 100 here as a remainder, that's the 100 we started from, and we are going to start with 85 again. Wow. And thus we will have, so just for the sake of understanding, I'm going to put here this 0, and then I'm going to put here 5, 8, 8, so on and so forth. Okay, just to make it clear. So these are the total number of digits which come unique, and then the repetition begins. So what can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total 16 digits are coming under my repeating block. So in fact, I'm going to write this in a recurring format. Let me use a different yes. So 1 by 17 is equal to 0.0588235294647, and the whole bar. This bar is very important. The bar indicates that these digits will, this block of digits, this entire block of digits will be repeated again and again, as we saw here. So this is how you perform the division for 1 by 17, and you come to this conclusion. So this was question number 5 from exercise 1.3, and there's one more question that we're going to see in this video for exercise 1.3. Yes, it's a question number 7. Very simple and straightforward question. We have to write three numbers whose decimal expansions are non-terminating and non-recurring. Okay, basically these are our irrational numbers. So let's go with our number 1. So it can be anything. It can be 1.2176582397658122 dot 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 dot. So note, in this number, this is a number. Okay, this is a valid number on our number line. It is non-terminating. So dot dot dot, it's non-terminating, and it's non-recurring. Non-recurring as in non-repeating. Okay, just for clarity, non-recurring means non-repeating, which means the digits in my number do not repeat. As you can see here, there is no pattern in this repetition. Random digits keep on coming infinitely after the decimal point. So this is a valid irrational number. Similarly, you can write down other numbers. Okay, I'm going to just blindly write. So I can even have negative numbers. So negative, let's say 100 dot 21, 21, 23, 24, 21, 23, 27, 28, 29, 30, and dot dot dot. So again, as you can see, there is no valid repetition. 2121 has repeated, but it has not repeated again. Okay, so there is no pattern in the repetition. Random digits are coming after my decimal point. So minus 100 dot this is again a valid irrational number whose decimal expansion is non-terminating and non-recurring, non-repeating. Similarly, let's quickly write another number. Three numbers are needed. So let's go with 57 dot 1, 2, 3, 4, 5, 6, 7, 8, 9. And don't again start with 1, 2, 3, 4, 5. Let's say, let me start reverse. So 9, 8, 7, 6, 5, 4, 3, 2, 1, and so on and so forth. So again, as you can see, this is non-repeating, it's non-terminating dot dot dot, and it's non-repeating. There is no pattern where you can put a bar and say that a certain block of digits repeat. So this is how you write three numbers with the decimal expansion non-terminating and non-recurring.